So today we're talking about Leap.js, and we're going to build a quick application showing off some of the features. This is called Build a Throw, and what we're going to do is we're going to try and build an app for that very visceral sort of interaction of picking something up and throwing it. And we're going to do this on top of the Leap Motion Controller, Leap.js, and WebGL and 3JS as well. And we're going to sort of go through and show some of the programming and debugging techniques in order to get there, and also how easy it can be to do just like a few lines of code to get to something that's like throwing something. So that's it. To get started with, here's what we're going to do. I just told you that. This is sort of the setup of Leap.js, where you've got the Leap Motion tracking installed on your computer. Can we focus this a little bit? Is this in focus? You've got the Leap service running there, and then you've got a WebSocket running the Leap service, which goes and connects to the web browser. And what this means is that there's a constant stream of Leap Motion data from the person's computer to their own web page, but without the need of a plugin or a Java applet or anything like that. So people can just open up a website that has Leap.js on it and get Leap Motion data with very little overhead. So that's quite nifty, and we'll show you just how to get data with it right there. So I'm going to open up this page, and the first thing you need is Leap.js, which you get to by going to js.leapmotion.com, and you get Leap.js like so, and you attach it to the top of your page. And then what you do is you open up your script tag, and you say Leap, that's a library, and you say loop. And what this will do is it will create a Leap controller object and connect that to the Leap service, which will then open a WebSocket connection and have frames start streaming through. And we can access those frames like so by opening up the controller and subscribing to the frame event. Now, each frame, to give you an idea, these happen quite quickly. The actual Leap Motion itself streams data at about 110 FPS, and your computer monitor updates at about 60. For like almost every LCD display updates at 60 FPS. And we can sort of test that really quickly by going and opening up the visualizer here and making sure we have a Leap plugged in, and then you can see sort of there's my face over there. And I can stick in a hand, and there's a hand, and if I press H, I can see over in the top left that there's a data FPS coming in at 100 or 110, and a render FPS of around 60. So what that means is that frames are coming through the WebSocket at 110 times a second. But Leap.js actually synchronizes to the browser's animation frame loop, which basically ties the motion of the library into the rendering of the page for solid performance, which is sort of the standard among like WebGL games and things like that these days. So what I'm going to do right now is I'm going to just show that we're getting frames. And we do that by putting a frame ID onto the output element. And we should be able to see this happening in a moment. Oops. Okay, so there we go. Those are our frame numbers. That's coming in fine like that. A frame has all sorts of data on it, basically hands, fingers, joints, just the positions of things, and then a few added properties which we'll get into later, such as grab strength and pinch strength. But I want to show you a couple nifty features right away. The first of which is the Chrome Profiler, which is very good for like if you want to figure out what's actually going on in your app. Maybe you're having some performance problems, maybe not. Maybe you're just curious. You can sort of see what's going on under the hood when I stick my hand in there like that. And this is available on like any Chrome. I think it's similar things are available in Firefox as well. And so what we're seeing here is a timeline, and it's got time going along this axis like that, and then we've got events coming in through here, such as what exactly is going on with this one, I'm not sure. So what these will be doing is we'll be having, here we go. So socket on message, that's happening at 110 FPS. And those sort of like, what you're looking at is the white space is idle time on your CPU, and the green space is used time. So you can figure out how much performance you actually have available in your app. And so we've got two loops going on here. One is the on-message loop with a socket, which is usually pretty lightweight, and then where most of your work is done is the on-animation frame loop, which happens slightly more slowly at 60 FPS. So that's what's going on there. That's a nifty tool. So now that we know how frames are coming in, there is another part of Leap.js which is interesting and good to have, and this is plugins. And you may be familiar with jQuery and its plugins library, or AngularJS and its directives, enough to know that it's pretty important to have easily plug and playable components on the web. And that's what we do with Leap.js plugins. Is you've got your frames coming in at a regular rate, and then you basically run each frame through a pipeline of plugins until they're present for your application. And these plugins can do things like transform data, or maybe recognize a gesture and emit an event when that happens. They're pretty easy to write. We probably won't get into them today unless asked for, but they're nice to plug and play. So that's cool. One of my favorite ones is called Bonehand, and what this does is it puts a hand onto a page, and it makes it very easy to get started with WebGL 3.js and with Leap Motion. So we'll start there. We're talk number 5. So the first thing we're going to do is we're going to bring in 3.js, and then we're going to bring in the Leap plugins library, which is a collection of useful plugins, of which Bonehand is one of them. And then we're just going to go here, and we're going to say use Bonehand, and we're going to pass in an options hash here, target el equals document.body. This is what Bonehand will do in this case, is create a 3.js scene for you with some lights and a renderer and a camera and a few other things, as well as the hands, so that you can see things right away. If you don't like that, you can also pass it in your own scene with the scene argument, or you can go in and you can actually modify parts of Bonehand, the parts of the scene itself, which is accessible on the Bonehand scope or object. So if I remember correctly, this should be all we need to do in order to see what's going on. There. So you can see I'm bringing my hand. There it is. It's a hand. That's cool and stuff. And if we look at the elements, we can see it created a canvas to put that hand on. And we can do 2 hands, but I need to use one of them. Or whatever. So that's what's going on right there. We have hands. And the next thing we want to do is we want virtual reality, because 2 dimensions is just not cool these days compared to 3 or more. So what we need to do is we want to bring in a couple things, VR effect and VR controls, which are some plugins that are, not plugins, they're libraries, part of 3.js, which make it really easy to use to set up VR with 3.js. So I'll show you where to get these real quick. You just go to github.com, you go to Mr. Doob, and you go to 3.js, and then you press T, and then you type VR controls, and that's your script file right there. So a little background. What I'm using is not straight up Chrome, not yet. I'm using Chromium, particularly a custom build which has the WebVR APIs built in. And there's a Chrome build that has these, there's a Firefox build that has these. They're pretty cool. And what they do is they add another method called, I think it's hud.getState, which gives back the position and orientation data of the Oculus Rift or any other HMD plugged into your computer. So these 2 libraries, VR effect and VR controls, they just connect to that getState API and make it and wire that into 3.js. So that's what we're going to do. And it's split off into 2 parts, and I'll show you them separately. Yeah.
That Mr. Doob link, it's Mr. Doob slash what?
Mr. Doob slash 3.js, and then you press T to get the file search thing, and you type in VR, and you'll see some interesting stuff. Okay, so here's the first one. It's VR effect. And so this is split into 2 bits. The first one being just the visuals, which means you need to see the left and the right eye separately, and they're actually rendered from slightly different angles. So I'm going to do that. And what I need to do is I need to create a new VR effect, and I need to pass in the camera, and I think it's the renderer, I'll figure it out, to sort of show how that looks. And so we need to get these out of the Bonehand plugin first of all, so we're going to do that. So we do that, and then what we want to do here is we want to say there's a new VR effect. And we want to pass in, if I remember correctly, the renderer. So this will take it, the renderer normally spits out the scene onto the canvas, and we're going to change how that happens a little bit. Now Bonehand has a render method by default, which is why you saw the hands, and it normally says render.render scene camera. We're going to override that with our own method, which says VR effect.render scene camera. And of course we need the scene of the camera, so we'll bring those in too. Okay, so if we're lucky, what this will do is it'll split the view into 2 left and right eyes here. And there we go. So because we're using the Chrome API, oh yeah, so another thing that Chrome does, or Chromium and the Firefox VR ready browsers do, is not only do they provide the state data of the Oculus Rift, but they also provide sort of the windowing data, which lets you, which shows the optical distortions for the edges of the field of view. So that's our VR effect, and then we need the VR controls, which actually moves the 3JS camera according to the Oculus Rift. Now we're passing the camera here, and all that we need to do here is before we do the render, we do VR controls to update. And now if we go back here and reload, that may or may not work. Undefined is not a function. I need to include the script on the top of the page. Boom. And we go here, get that back again. And so, okay, what we've got is I've got my lead motion here, and as I move my Oculus Rift, is that on the camera, I guess? Mm-hmm. Okay, great. As I move my Oculus Rift, you can see that the hand is actually moving its position. We're far from done, but these 2 API endpoints are indeed working. So what we want to do next is we want to actually change the position of the lead motion, because up until now I've been using it sort of in desktop mode like this, whereas what we really care about is using it on the Oculus Rift instead, from quite a different point of view. So in step plugin number 2, this is called Transform. Now what Transform does is it makes it very easy for you to arbitrarily change the position or orientation or any of it or scale of any hand in the 3JS scene. And it also has a special mode just for VR where you can say, I don't want to do my own transformation, I just want you to make it capable of being VR ready. So what we're going to do is we're going to start using that plugin now. And I should mention that the order in which you call .use on plugins is pretty important, because this is the order by which the frame will pass through them. So we're going to put transform before Bonehand so that the data actually gets mutated in the frame before it gets rendered by the Bonehand plugin. So let's do that. And we're going to pass in this here. You'll notice that we've got method chaining going on, so this returns the controller, this returns the controller, etc. That's pretty convenient. And we're just going to pass in one option here, VR:true. That should be all I need in order to be able to use these classes. Yeah, there we go, right in front of my face, like that. I'm going to use these glasses because they're a little bit easier than wearing the Oculus Rift and talking and coding at the same time. What you can see is if this was the front of my Rift and I turned my Rift, it would all sort of work out. There's one other thing we need to do in order to make the VR effect work correctly. Whereas if you notice very closely, here I go, I've got my hand right here, and if I were to turn my head, then the hand disappears from the field of view. Actually, let me demonstrate this a little better with the Leap Motion on the Rift. One of the things about this is that it'll get a black background. Let me recenter it. So there I've got my hands. And because the Leap Motion is actually sticky taped onto the front of the Rift, what happens when I move my head is the hands disappear outside my field of view, which is very strange. It's not what I want them to be doing at all. I want my hands to be mine, not moving on their own. So there's what we want to do is we want to actually use the scene hierarchy of 3JS and parent these hands to the Oculus Rift. And the way we do this is with another part of the API of Transform. So let's grab that plugin, and then I'll show you the thing. Transform's there. And we want to set this option equal to the camera. And this means that the camera's transform will be applied to the hands, as well as the VR transform. So now what should happen is when I rotate my head, the hand stays in front of me as I would expect it. Now it's properly my hand. And this is pretty important.
So
Yeah.
there's a question real quick.
Yeah.
So before you added the transform library and your hands didn't get larger or smaller, when you move them closer or further to the Rift, is that the functionality you added?
So let's open this up here. I'll see if I can. So you're asking about the hands changing size. So the transform isn't doing anything to make this special right here, because when I go farther away, 3JS says, oh, that's a point that's farther away. I'm going to render it farther away. It's going to look farther away. So that's all just like if you position an object in 3JS, it looks far away. And to be truthful, there's no actually scaling going on here. It's just far away. That is, the position between the bone and the camera is far. What the transform did is it made it so that the hand looks like this right now instead of like upside down like that, which would be if you had a bottom viewpoint. Does that clarify things a little bit? Good time for a recap. So what we've done right now is a basic VR setup. We haven't done any application-specific code yet. We've just been sort of like, okay, here's how I get a hand. Here's how I get VR. I've written about not even maybe 20 lines of code if you leave out the white space. There's this bit I didn't talk about, which lets you zero the sensor and set full screen with a hotkey. That's pretty simple. So basically, we have a very simple setup for starting to code and starting to build my app right now. But our goal here is to throw something, which would be sweet. And we have a whole bunch of sort of interesting things and decisions coming up because we need to figure out how to pick something up. What does it actually mean to pick something up? Which is actually a fascinating question with a great amount of depth. And then we've got to like sort of build the things that you can pick up and allow them to be picked up. And then we have to sort of, when you let them go again, what happens? And the answer to that is, of course, physics happens, and it goes from there. And it turns out that none of this stuff is actually too difficult either, if you just sort of do it in the most straightforward way. So the first tool I'm going to show you is called Leap Data Plotter. And we sort of built this early on in Leap.js because here you are working with all this data coming in at 60 FPS, and it becomes quite difficult if you're just spitting that out into the log all the time to figure out what the heck is going on. So we're going to use this to look at pinch strength and sort of see when to grab the sphere. Pinch strength, by the way, is a measurement of how much any two fingers are close to each other. and it's a scale from 0 to 1, and we want to think, okay, what would be a reasonable number for pinching? What feels good? So we want to practice it and see what it looks like. So we're on number 8 here. Let's see, so the first thing we do is we go back to js.leapmotion.com and we bring in Leap plugins, but we've got a util library now, which includes only Leap Data Plotter. And we're going to set that up. Let's go down here. For our plotter, equals new Leap Data Plotter. Sure. Do I need to pass in the control here? Anything like that? Oh, okay. And then what I'm going to do is I'm going to say, when there's a hand, I want to plot the pinch strength. So let's open up the Leap controller, and we had the frame event. We also have the hand event, which fires for every hand on every frame, saving you a bit of your own looping sometimes. So we'll do that and that. Yeah, and then we can do plotter.plot pinch strength, and then we do hand.pinch strength, like so. And then we have plotter.update, which I guess I forgot to remove the last time I did this talk. So we've got plotter.update there, we've got plotter.plot on every hand, and then we've got the plotter itself instantiated. So let's see if this works. I need, not those, but these guys. And so you can see up in the upper left corner there's a nice 2D canvas with a bunch of zeros on it. And it should be, if I start to pinch, you can see this graph. And the way you read this is you've got the sort of the label in the upper left, and then you've got the current value right here, and then you've got the max and min all-time values. So it's kind of hard to see on the screen. Can I make it bigger? Yeah.
Why attach the hands to the HMD? Our hands are untouched, our heads, if you look away, the hands disappear.
So the reason for that is because the HMD itself moves. So what's happening is you've got these two things. And when you look away, both the HMD is moving, which you'd expect, but also this number between the Leap motion's field of view is moving as well. And so if you stack them up, they invert each other, and you get what you need. Without that, it makes it look like the hand is moving twice as fast as it actually is. Beyond that, I can recommend trying this out and playing with it to sort of get a very, you'll see what it means. It feels completely wrong if you don't have that in there. The hand sort of travels away on its own. Yeah. I'll think if I can think of a better way of explaining that as we continue to talk. But here we are, we've got pinch strength. We can see that when I pinch it's at 1, when I unpinch it's at 0. So we might say when it's passing 0.5, that's when I've grabbed something. And that would be the definition of grabbing the sphere. So that's pretty cool right there. And it's kind of a useful library to know about. Yeah. So now we get to the fun stuff. We know what we want. We have a basic boilerplate. We want to actually have things to pick up. So we're going to make a sphere bank, like so. We're going to say, well, maybe we want to support up to 4 hands in our application, just to be liberal. And then we can say, so we want to create 4 spheres, so we can say our sphere equals new 3-dot mesh. And we want to pass in a geometry and material, sphere geometry, and this sphere geometry, what's it need? It needs, so the nifty thing about this, and something I mentioned about transforms, not only is it doing perspective, but it's also doing units. So the Leap motion controller comes in millimeters usually, which is pretty nice when you're working with small distances in hands, but the Oculus Rift and such expect meters. which is also pretty nice. So what this does is transform, makes everything into meters, and so when I type in 0.03 here, what I'm saying is I want a sphere that's 3 centimeters big, and this is about 10 centimeters, so a sphere will be about a third of my hand, which is nice. And then to make it nice and spherical, we'll add about 20 segments in each angular dimension. And then we can do 3 dot, we'll put in a material here. We'll just do a nice simple echelon material right there. And then we want to add these to the scene. Scene dot add sphere. And that might be all we need at first. We should be able to see some spheres. Their position will be a little off, so we can't see them right away, unfortunately. So now we want to actually figure out how to make the pinch. So what we do, I mentioned plugins before. There's another plugin that I wrote for this, which emits 2 events for pinch strength. Basically, when it crosses 0, then it says you're pinching and emits a pinch event, and when you go back, it says unpinching and emits an unpinch event. So I included that right here. It's a pretty short plugin. I encourage you to look at the source, the GitHub repo. But there it is. And what it means is we can do this. Loop controller on pinch. Root function in a hand. There we go. And what we want to do when we pinch is we want to take a sphere and attach it to the hand. So we're going to write this into 2 steps. First, we're going to do the data. We're going to say this sphere is attached to the hand, and then later on we're going to write a loop which says find all the spheres which have hands attached and position them. So all we need to do right now is use this. So this is sort of like jQuery data. It's like I'm going to say take this hand which persists between many frames, and I'm going to attach this piece of data to it, which is our sphere. So we're going to say var sphere equals spheres.pop. That should be pretty simple, and we can do the same thing for unpinch. And then we can do sphere equals and data sphere. And then what we can do is since we got a sphere, if there's no sphere, we want to get rid of it, or if we don't really care, so we can say return. And then what we want to do is we want to put it back into our sphere bank, like so. And then we can take it off the hand, finally. Something like that. So, what this does is means when we're doing a pinch, there will be a sphere available on hand.data sphere. And so we can make use of that here on our frame loop. And you'll notice as I code this, I'm breaking this up into lots of little tiny loops, which I think is pretty good practice for application development. So you've got a loop, I've got 1, 2, 3, 4, 5 different loops going on here, which is nice because if you have everything in one giant loop, it just gets really hairy really quickly. And here you can split up little independent features. So I've got my function. This guy right here, I'm going to say, actually we need this for hand. And what we can do is if hand.data sphere, and we're actually going to switch this from early return so we don't get Christmas tree effect of nasty loops. And then we're going to say, and then we're just going to position it. So we're going to say sphere position let's do for array, which allows us to read in the loop.js API, which is an array, and convert it into a Three.js, a vector3 position. And so we're going to just take in the palm position here, which is sort of like the middle-ish of the hand. So So if I did everything right, what's going to happen is we're going to go in there, we're going to do a pinch, it'll take a sphere out of our spheres array, it'll put it into the hand, and then it'll start making it match the palm position. So let's see if that's actually what happens. We are on page number 9 here.
Did somebody say, shouldn't that be if sphere return?
If sphere return.
Exclamation point.
Exclamation point.
Now there is an exclamation point.
On the unpinch.
On the on page. Yes, there we go, thank you. That is a bug, but it's not the bug that's stopping us here, unfortunately. Let's go on. Let's just see if this is happening. We added this to the scene, we did, they're there. There's not actually anything going on. Oops. What we can also do is we're going to spit out our pinches here. So there's the pinch and the unpinch. And so we could even go here and we could say, show me the sphere that you're pinching. Show me that it's actually there. Interesting. So that's not going to work. And there's our bug. Spheres dot push sphere. Boom. So what just happened? We pulled it out. It was at 0, 0, 0, which is like the position of my head, I think, usually something like that, depending on when you zero the sensor, which is now what. Yeah, there it is. Let me just move back a little bit. And so I can pick up a sphere. And I can't throw it, but I can pick it up. So every time I pinch, the sphere enters the position of my hand. And you can see I can do multiple ones. That's pretty nifty right there. And one other thing we'll do, just so there's not this giant thing happening there that's not very cool, we'll just say sphere.visible equals false. Sphere.visible is true. Grab this again and do that. There we go. Alright, that's pretty neat. So we're almost there. We can pick things up. We just can't throw them. We can just sort of let them go and they disappear again, which is, I guess, not that cool. So last step is physics. And a lot of people, okay, speak up, he says. So with physics in JavaScript is a bit of an interesting situation. There's a number of different libraries out there. They are in various states of repair. Some ported over from C++, some not. MoJS, Visit.js, and there's sort of a new one ported over from Flash called OMO.js. And these are all pretty interesting, pretty exciting. But I haven't really found one that I'm like, yes, that's the library that I want to be using. But as it turns out, if you want to do sort of a limited physical thing, then you can build it yourself without too much trouble. And if you sort of scroll through the 3JS examples, you can see partial implementations of this and that. You can find a sweet wind effect or a physics. So that's what I did. And this is a very simple implementation of Newton's laws in one dimension to give us momentum. And knowing how to build your own momentum is actually pretty sweet, because then you can do like a little inertial scroll or whatever else. And it's just this neat trick. So what we've got here is Newton's laws. My new position is going to be my old position plus my velocity times time plus my acceleration times time squared. That's what this is. We've got no acceleration, there's no forces, there's no gravity. So we're going to throw away this last term here. And then we've just got x plus change in x. And it's called relay integration because it's designed specifically for this. Because we're working on a frame-by-frame basis, we can store last position, and we can know the difference between how something's moved between two frames very, very simply by keeping track of, on every single frame, both the sphere's position and its last position. And that means that my hand will be setting its velocity without ever making a variable called velocity. So let's see how that works. I want to look at the complete version of that. So, here we are, talk number 11. So here we are, we're in the render loop now. And what we're going to do is we're going to run our physics engine right before we render. And what we're going to do is we're going to find all the objects which can be affected by physics, and we're going to put them in their right places. So for I equals 0, I is less than spheres length, I plus plus, and we're going to have our sphere right here, and we're going to say sphere equals spheres I. And then what we're going to want to do is I'll add this variable in, which is called .pinched, which we don't track right now, but if not pinched, continue. And then, nope, we want this the other way around. So if it's already in the hand, we don't care. It's being handled by leap motion. And if it is not in the hand, then we want the physics engine to take over and have it move on its own. That'll be the momentum of the throw. So if it's not pinched, here we are on line 140. And what we're going to do is we're going to do that Verlet integration. If you're not familiar with the 3JS API, it's pretty much a very good matrix math implementation for JavaScript, at least until we get ECMCA script 7, whatever has the vector math implementation. But we go in through here, we're going to set this new position vector to the difference between two existing positions. So we can take in sphere.position here and sphere.last position here and do that. So now we've got the change in position, and what we're going to do is we're going to add a little bit of drag so that it slows down on every single frame. And we're going to do that by taking, so this is x, y, z, and we're going to multiply each one of those by a scalar. Multiply scalar, and we're going to just do 0.94. So this means it'll slow down by 6% every single frame. And then what we're going to do, now that we've got the change in position, we're actually going, seeing as this variable is called new position, we want it to be the new position, we're going to add the current position to it, sphere position. And this is the new position we're going to set. So we want to track the old last position first. So we want to do sphere.last position equals sphere.position.clone. Now, this is an interesting part of the 3JS API, is we're actually taking this existing position variable, we're duplicating it, and we're storing it here. So we're basically saving that so that we can use it later, which is the next time this loop is run, which is over there. But anyway, we're still on the first time this loop is run, which is right here, and we're going to say we're going to set the sphere position. So we're going to say sphere.position, and we're going to do copy the new position. And this means that x, y, and z variables in the new position will be put onto the current position. That's a lot. There's a little bit of cleanup work we have to do, and we'll go through this run one more time, and then we'll run it and see what it looks like. Okay, so we need to track the pinched state. We need to make sure that this last position is always valid, because on the first run, I believe it's not. And then we should be good to go. So let's go over here, let's figure out, let's make sure this variable is always what we want it to be by just going up here. I left this in here from last time. Sphere.pinched equals true. Actually do that. Sphere.pinched equals false. And then we've got over here, we've got sphere.last position equals sphere.position.clone. That happens right when the sphere is first created. So this way, this variable will always be valid. So that's cool. So what should happen? We go through, we loop through all our spheres, we find one that's not pinched. We do the integration, we add its position, and we set it up. Let's see if this works. Bingo. So I do the pinch, sets it up, and let go again. And while I'm pinching, it's always setting that last position. And so when I let go, it slowly adds a drag. I can throw it any way I want to throw it. That's it. We've accomplished what we want to accomplish. Jump. Wow. There's some sort of bug in here. But we can go to the cheat version here, which does basically the same thing, but without whatever bug that was, and lets me throw it like so. There we go. In conclusion, that's our app, that's JavaScript, and we have time for questions if anybody has questions.
What's the IDE?
So I'm using RubyMine for this. I started out in Ruby. I think they also make one called WebStorm, which is just for JavaScript. Yeah. Yeah, I'm a big fan. I've been using it for a few years.
Xcode? These are
I haven't used Xcode for web stuff. I don't know if people do or what they think of it, so give it a shot. What's that? Yeah. That's it. I hope you enjoyed the talk. Oh yeah. We have some other things we can show you too. Now that I remember, which is something we've been sort of working on a little bit. Which is Mozilla's been working on sort of a VR experience and sort of what a VR browser or the VR web would look like. If you haven't seen it or heard of it, you should check it out. It's pretty cool. It's mozvr.com. And it's designed to work with VR browsers. Interesting. This is a new version that I haven't seen before. But anyway, we took this and we decided to see what would happen if we could leak enable this website. So we have our own version on our stuff, leapmotion.github.io/hero. Let's see if I unplug this controller, plug in this controller, we should be able to see a quick demo. So we can see the same hand brought in here. This is all built in 3JS. It works with either the Mozilla VR Nightly or the Chrome VR Nightly. And I can sort of see the background going on over there. And this is our own custom branch, which has a hand built in. It lets me do things like push these nice buttons right here. So what I can do, for example, is I can go over and I can visit this page right here. That should take a moment. That should load up. And then normally the way you'd interact with this would be you'd press the space bar and bring up the menu. But in this particular version, what happens is you bring in your second hand, and your menu pops up just like that. And then you can reach in and go in and press something. Like so. It's still very new. There's still some performance issues on both the browser side and the MozVR side. But this is sort of a sneak peek of some interesting things that we're working on.
How does one get to that? Is that live anywhere?
It's not really linked up anywhere, but it would be leapmotion.github.io/HIRO.
Okay, leapmotion.
Yeah, I'll put it up here on the screen in a second. And this is another library that we've been working on recently. As part of the LeapJS widgets project. What it does is it allows you to go in and actually interact with the plane like so. When you bring your fingers in, there's an intersection point right where the fingertip touches the plane, and then you can move things around. So that's quite useful if you want to start building some web UIs. This would be a good starting point. And you'll notice that each of these planes uses the same relay integration scheme that we just looked at. Yeah, there's a little hidden feature here, which we can take some hands, so that's that. Yeah. Let's go back to this guy. Is that it? Are we done?
How do you find the performance on
What's it? What is it?
How do you find the performance on the RMVP?
RMVP.
RMVP. Lowercase r, capital M. Clarification.
Right mouse button. RMVP, like so. Oh, like it's pretty good. It's not terrible. I'm able to get 60 FPS on this quite reliably. Let me just show you. If I open this up in Chrome instead of
Retina MacBook Pro.
yeah, okay, that makes sense. So I can run like any 3JS example or this project itself at 60 FPS pretty happily. So that's pretty good. There are times it is possible to slow it down. There are times when that happens, but it's by no means something that's like a deal killer. So I'm pretty happy with this computer as a graphical interface. Compared to that, like the MacBook Air, I have friends with the MacBook Air, and they can't run the same site. So it is important to have the power of the MacBook Pro. There's a good talk by Brandon Jones, who's behind the Chromium build, on how to sort of work with these APIs and improve performance. Let's see if they're up right now. He just gave this recently, so it's bit.ly/sfhtml5 videos, where they just had a night on, 2015 isn't here yet, but at some point it will be, and we'll talk about sort of how to work with Chromium and the WebVR builds and sort of how you can get extra performance out of that.
And that at WebVR on GitHub before we forget.
So that's what's up on the screen right here. This isn't the official WebVR, this is just our sort of take on it. leapmotion.github.io/hero. That's a good place to sort of check out sort of what we've been doing and trying to figure out how to make it go in the real world. And it's sort of built up out of these component projects like Leapmotion. Like here's one of the projects that goes into it. There's this guy here, which makes it pretty easy to go in, poke things, and move them around. Got that. What else is there? Yeah, there's this. We looked at this before. Yeah. Am I forgetting anything?